All right, hello everybody. Welcome back to Math Background for Machine Learning. In the past few classes, we've talked about maximum likelihood and maximum entropy as two different ways to fit a distribution to some data. So in maximum likelihood, you pick a family of probability distributions that has some parameters, and you adjust the parameters to maximize the probability of some observed data. In maximum entropy, you choose a vector of moments, the expected values of some statistics of your distribution, and you optimize the distribution to maximize entropy subject to matching the observed moments. So in simple cases, we can solve those maximization problems exactly, for example, by taking the derivative and setting to 0. More often, what we need to do is optimize numerically. And so I figured we're going to do optimization in greater detail toward the end of the mini, but to let you solve maxent and maximum likelihood problems, we're going to spend some time today going over what is probably the single most common optimization algorithm in machine learning, which is gradient descent. So here are the lecture notes on gradient descent. All right, so a lot of times in machine learning, our optimization problem has the following form. We have some parameter vector W for weights, and we have a loss function, L of W, and we want to minimize loss. And we can write that often as a sum of terms, L0 plus the sum from 1 to t of LT. And so again, W is our vector of parameters. Let's say it's d-dimensional. There's some possibly constraint set C that tells us the feasible values of our parameter vector. And then we have these terms, L0 through LT, that encode the problem data. For example, we saw a while ago the problem of least squares, where we have a matrix which has, let's say, t rows and d columns, and a vector with t rows, and we want to find the parameter W that minimizes the squared 2 norm difference between AW and B. And so to express this as a sum of terms, we can have one vector AI for each of the rows of the matrix capital A, and the objective then is the sum over all rows of the squared difference between at.w and bt, right? So for each row, you're trying to make the output of that row be equal to the corresponding element of B, and you penalize yourself by the squared difference. And we also talked about regularized least squares, where we add, so here we're just using L1 through t, and we're setting L0 to be just the constant function 0. We could set L0 to be some multiple of the 2 norm of our weight vector, and that would give us regularized least squares, which we also talked about a few lectures ago. And so you can see here that we've split up the terms into L1 through capital T, which play one role. These encode the rows of our matrix A, and L0, which plays a different role, which is the regularizer. And a lot of times in this sum of terms form, we have this distinction between stuff that is general across the entire problem, that goes into L0, and stuff that is one per data item. So for example, one per sample from a probability distribution, or one per row of the matrix A. And so, you know, that's not required, but again, it's a common form of an optimization problem in machine learning. All right, another example is maximum likelihood. So we saw before that with data 1 through capital T, x1 through x capital T, if we set LT of W to be the negative log of the conditional probability of the tth sample given our parameter vector W, then the sum of all of these logs, that's the same as the log of the product of P of xt given W. And because we're assuming the x is to be conditionally independent given W, that's the same as the log of the joint probability of all of the x's given W. And so minimizing this is the same as maximizing the likelihood of our data given our parameters W. And again, we can set L0 to 0, and that gives us maximum likelihood, or we can choose L0 to be a log prior for W, and that would give us maximum a posteriori. All right, and so that's a couple of examples of this sort of sum of terms form. And again, not every optimization in machine learning has this form, but a lot of them do, and so it's useful to have methods that can take advantage of that form. All right, so I should mention that one of the differences between machine learning and a lot of other uses of optimization is that in machine learning, we are often happy with not particularly accurate solutions to our optimization problem. And that's not just because machine learning people are happy-go-lucky kind of people. It's because there's often not a benefit to extreme accuracy in machine learning. So this happens for two reasons. One is that often the thing that we're optimizing comes from a training set, and we don't actually care about training set performance. We care about test set performance, generalization performance. And so it often happens that we have this phenomenon called overfitting, whereas the training set loss gets lower and lower. It'll keep getting lower forever as you keep optimizing, although it'll asymptote to some value. But after some point, the test set error, right, it'll keep going down and down and down, but at some point it'll stop going down and it'll actually go back up. And so we want to stop. This is called early stopping. We want to stop before it goes back up. By the way, it's not at all obvious that early stopping should help. It's kind of a deep result, and further machine learning courses will talk in excruciating detail about why it might happen. But for now, all you need to know is that it exists. And so early stopping means you stop before you're done getting to the best possible value of your loss function. Another one, so even if you don't need early stopping, a lot of times the data in our optimization problem, it comes from random observations with noise in them. And so, if you only know your observations to, 1 part in 100, it doesn't really make sense to optimize your parameters to 1 part in a billion, right? So in particular, all that's required is that you optimize your parameters to a degree such that they're not the largest remaining source of error, right? And so both of these things, both of these factors, the factor that we care not about training set performance but test set performance, and the factor that we have noisy data and so there's no point in getting a hugely accurate solution. Both of these mean that in ML we often don't need a solution that's accurate to 1 part in 10 to the 12. And so that's useful because it means it opens up a lot of optimization algorithms that otherwise we would not be able to use very well. All right, so because of this, we often use what are called first order methods for optimization in machine learning, and those are methods that are based on gradients. So the reason that a gradient is useful for optimization is something that we talked about in the first mini. The gradient is the direction of instantaneous steepest ascent of a function. In other words, locally in some tiny region of the function, if you want to increase the function as rapidly as possible, you go in the direction of the gradient. And conversely, if you want to decrease it as rapidly as possible, you go exactly opposite the direction of the gradient. So here are a couple of pictures, right? So here is a loss function, and here's a contour plot of that same loss function. So you can see that darker colors of copper correspond to smaller values of the loss function. And then if we take that contour plot and flip it so that we're staring straight at it, here it is, and we can take a point here. and look at its gradient, which is this blue arrow, and you can see that we're increasing the function, as we said, as rapidly as possible by going in the direction of the blue arrow, or decreasing it by going in exactly the opposite direction. We can also see that if we take a line whose normal is the blue arrow, or in multiple dimensions, a hyperplane whose normal is the blue arrow, that hyperplane is going to separate, at least locally, directions of increase from directions of decrease of the function. So in other words, the gradient is normal to the level set, and this hyperplane is tangent to the level set. And we can actually derive that if we take a look at the local Taylor expansion of our loss function around our current point, right? So our loss is equal to the loss at our current point plus the distance we move, the direction we move, dotted with the gradient, right? And so that this says that we're going to increase the function exactly when the direction we move dotted with the gradient is positive. That is to say, when we're on this side of the hyperplane up here. All right. And the same thing, we can say here, this is the hyperplane whose normal is the gradient, and it's going to separate, at least locally and approximately, the directions of increase from the directions of decrease. All right. So because the gradient is the direction of steepest ascent and the negative gradient is the direction of steepest descent, there's a simple optimization algorithm that says, well, if you want to decrease our loss function as rapidly as possible, take a step in the direction of the negative gradient, right? So we take our weight vector and we subtract a multiple eta of the gradient. And eta is called the learning rate or the step size. And we're going to just repeat this update over and over. So we take a step, we reevaluate the gradient at the new location, and take another step. And so there's a trade-off in choosing the step size. Obviously, you want a big step size so that you move quickly. But if you choose the step size too quickly, then the local Taylor approximation is going to stop being good, right? So if we have some curved function, the Taylor approximation is only going to be a good approximation locally in some area around our current weight vector. And if we step beyond that, the function might actually increase, and we might hurt our loss function value instead of helping it. All right, so that's gradient descent. And we almost never use plain gradient descent. Sometimes we do, but what we typically use is a modification of gradient descent called stochastic gradient descent, which we're going to take a look at now. All right, and so if you remember our sum of terms form for the optimization problem, right? Suppose capital T is like a billion, right? We have a very large training set. Then just computing this gradient can be impractical, infeasible, because in order to do that, we have to iterate over all billion of our training examples in the maximum likelihood problem. And it might be, non-trivial. It might take a little while to compute the gradient of each one. And so, a billion times even a few seconds is going to be a long time. So what we do is we take advantage of the fact that we only need a pretty inaccurate solution. And we say, okay, we don't actually even need to compute the real gradient. What we need to do is compute a vector g, which on average is going to be the gradient, but it can have a significant amount of noise in it, right? And you can see that that's actually going to be sufficient. It'll be helpful to optimize, right? So if we take W and update it to W minus eta times G, where G is our noisy gradient estimate, right? The expected value of that given W, well, we can get an approximation to that by replacing L with its Taylor approximation. So the Taylor approximation says that it's going to be L of W minus well, plus g dot the change, and the change is minus, it's going to be L of W, that's the point at which we're making the Taylor expansion, plus the gradient of L at W, that's the first order term of the Taylor expansion, dotted with the change, and the change is minus eta times g, right? And since expectations are linear, we can push the expectation in through to get L of W minus eta E of g given W dot the gradient. And we know that the expected value of the gradient given W is actually, the expected value of g given W is actually equal to the gradient. And so this is actually L of W minus eta times the squared norm of the gradient. And since the squared norm is positive, this is going to be less than L of W, at least as long as this Taylor expansion is sufficiently accurate. Let's see. So 2 questions. Somebody's asking about regularized least squares. Where did we discuss it? I think it was close to the end of the second mini. We discussed it as an example of how to do matrix derivatives. So we actually had the least squares loss function several places in the notes on matrix differentials. And somebody else is asking about how to choose the best learning rate. That's a good question. And I think if you want to skip ahead to block 9, you'll see the answer. But I think I'll wait to answer it until we get to block 9. Oh, somebody's asking about local optima versus global optima. Yeah, that's a great question. So gradient descent and stochastic gradient descent are only going to be guaranteed to find local optima. In a lot of the problems that we've seen so far, there's only the global optimum. So for example, if you have a convex problem, there's only that global optimum. In general, in machine learning, it is a big and difficult question to figure out whether you've got a good enough local optimum. In particular, there's a lot of work, like right now, about deep learning and how in a lot of deep learning models, it seems like you get to a good local optimum, one that's nearly as good as the global optimum. And actually, nobody really understands that. There are a few special cases where people understand. So for example, in the past couple of NIPS, there have been papers showing that certain non-convex problems have all of their local optima are pretty good. But in general, that's a difficult question. It's the subject of a lot of current research. What people will often do is, just because they can't afford to do any better, they'll run stochastic gradient descent and cross their fingers and hope for the best. Or people will use a convex relaxation. They'll change the problem to make it convex so that you can get to a global optimum. Basically, all of the different ways of dealing with it are very interesting, but beyond the scope here. Somebody's asking again, what's a sum of terms? So the sum of terms is exactly and only this form here, where our loss function is a sum of smaller loss functions. And there's a couple of examples here, least squares and maximum likelihood. And both of those actually, like maximum likelihood or a slight generalization, maximum conditional likelihood, will give you almost like a huge pile of examples, including like regression and a lot of classification problems like logistic regression. So if you Google those phrases, you'll get more examples. All right. All right, so stochastic gradient, right? We said that if we can figure out a vector G, which has as its expectation the gradient, then we'll be able to run gradient descent with this vector G instead of the real gradient, and it's still going to work, right? That's what this derivation says. And so as long as we can find this noisy estimate of the gradient more efficiently than evaluating the true gradient, we can win. We can make stochastic gradient run much faster than ordinary gradient. Now it's a trade-off, right? Because we're going to go slower because we're using noisy estimates of the gradient, but we're going to go faster because each step is going to take less time. And so what you'd like to do is find the least noisy estimate of the gradient that you can compute the fastest. And so that's actually an interesting subject of research for a lot of problems, to figure out these estimates quickly. Oh, I should point out as well, the noise can actually even be beneficial, right? So if you're about to get stuck in a local optimum, the noise can actually bounce you out of that local optimum so that you then have a chance to go down to the global optimum. If you're lucky, there's, not usually a guarantee about that. Oh, right. So somebody's asking about the difference between convex and non-convex functions and convex and non-convex optimization. That's actually something that we're going to cover, I think, in a little bit more detail later in the mini. But the quick version is, if you have a function that looks like this, that's called a convex function. And if you have a function that looks like this, that's called a non-convex function. And the official definition, right, the picture is, the picture is nice, but it's not the formal definition. The formal definition is that if you take, if you take this point, if you take a point on the function and another point on the function and connect them like that, this line lies entirely above the function. Whereas here, if you take a point on the function and another point on the function and you connect them with a line, the line is sometimes above and sometimes below the function, right? So that's the definition of convex and non-convex. And you can see that this convex function has a single global optimum. And you can see here that the non-convex has a local optimum as well as the global optimum. Now, in a one-dimensional input function like this, it's pretty easy to see everything that's going on, so you can see all of the local optima and the global optimum. In general, in high dimensions, what's going to wind up happening is that there could be arbitrarily many local optima. The function could be, folded and creased in all sorts of nasty ways to make it difficult to figure out where the true global optimum is. And so it's computationally quite a difficult problem to get to the true global optimum. And what we do when we're using gradient descent, so gradient descent is guaranteed under, fairly general conditions to get you to a local optimum of your function. And we either have to just hope that the local optimum is nearly as good as the global one, or we have to assume something more about our problem so that we know that there's only the global optimum to find. Oh, yes, somebody's asking about the acronym MAP. MAP stands for maximum a posteriori. We covered that again in the first mini. It's like maximum likelihood, except that you assume a prior distribution on your parameter. And again, the notes on maximum likelihood, which I think was the last set of notes in the first mini, will give more detail. If you choose, somebody wants to know, if you choose too large a learning rate, is it possible to have something bad happen? And the answer is yes. Yeah, you can even actually have gradient descent diverge, which means that instead of having the parameters W converge to a local optimum, getting closer and closer, they'll actually get farther and farther away over time. They'll like jump back and forth. You can think about it like this, right? So here's an example of a function. If you take it, here's your point, your gradient is pointing that way, right? And so you take a step. If you take a small step, you'll go down to the to the optimum. But if you take too big a step, you'll go across the optimum, right? And if it's a little bit too big, you'll just go back and forth like that. But if it's really too big, you could go like that, and then like that, and then like that, right? And go farther and farther away over time. And again, how do we choose the learning rate? Wait until a few sections down the road, and I'll talk about a couple of different ways for choosing it. Let's see. All right, so thanks again for asking good questions, and I think that's all of the ones that are up on Piazza now. So, so we left ourselves with the task of computing a vector g whose expected value is the gradient so that it's a noisy estimate of the gradient. And so how are we going to do that? Fortunately, it turns out to be easy. At least it's easy in this sum of terms form of the optimization problem. Basically, we just choose a single term randomly from the sum and take its gradient and scale that by the number of terms. So to see how that works, let's take a problem where L0 is 0, so that we're just optimizing the sum from I equals 1 to t of Li of w. And so what we're going to do is choose an index I uniformly at random from the set 1 to capital T, and take our gradient estimate g to be t times the gradient of the ith term in our loss function. This is going to be right because if we take the expected value of the gradient of the ith term, well, what that's going to be is the sum over all possible values of I of the probability of that value of I, which is to say 1 over t, right, times the value of the sample if we choose I, which is going to be just grad LT if we choose the teeth, if I is equal to t. Right, so if we take the expected value of the gradient of a random sample, that's going to be the average value of the gradients of all of the samples. And so since g was t times this gradient, the expected value of g just cancels out this 1 over t, and it's going to be the sum of all of the gradients, which is to say the gradient of the original loss function. Right? So it's kind of a cool trick. By choosing a single term at random and evaluating it, we get a noisy sample of the full gradient. And it could be very noisy, right? It could be that each individual term is not very representative of the whole sum. But on average, if we sample enough, we're going to get exactly, we're going to converge to exactly the right answer. Oh, somebody was asking, what do I mean by the noise? So this is precisely the description of what the noise is. So in general, when I say that a random variable is a noisy estimate of something, that's going to mean that its expected value is the something, and the noise is the difference of the random variable from its expected value, right? So here, right, what we're trying to do is estimate the gradient of L, and we don't get exactly the gradient of L, right? We get t times the gradient of one of the terms, and so the noise is the difference between our estimate and the thing we're trying to estimate. Another example for noise would be, let's say that you're trying to measure some physical quantity, like the length of a specimen, the length of the leaf of a plant. So if you ask 5 people to measure that leaf, they might all come up with 5 slightly different answers, right? Like one person might say that it's 17 millimeters and another might say it's 18 millimeters because they, hold it up to the ruler slightly differently. And so there's some true value of the length, and hopefully on average when people measure it, you'll get the true value, but each person who measures it will get something slightly different, and that difference is the noise. All right, so let's put it all together now. We've got a vector g, which is equal to t times the gradient of a random term, and the expected value of that vector g is the gradient of our entire loss function. And so in stochastic gradient descent, we're updating W to be W minus eta G, where G is a sample, right? G is this noisy estimate. And so that's the stochastic gradient descent algorithm. We repeatedly sample an index uniformly from 1 to capital T, take the gradient of the ith term in our loss function, scale it by t to compensate for the fact that we only took one sample, multiply it by the learning rate eta, and subtract it from W. And we keep doing that over and over and over again until we're tired. Somebody wants to know a difference between a noise and a residual. They're actually really similar concepts. Residual is usually the difference between an estimate and the truth, right? Like some estimate that we compute, not necessarily like it could be the output of some optimization algorithm. Whereas noise, we're typically thinking about a single random variable, its difference from its mean. And so, you know, they're almost the same idea. It's just slightly different connotation for what we're talking about. Usually in the connotation is basically that the residual, there's some more complicated procedure that we're using to compute an estimate, whereas noise, we're just thinking of like a single sample and looking at the difference from its mean. But again, that's only the connotation. They're fairly similar concepts. All right, so so here is the stochastic gradient descent algorithm. And again, this is maybe the single most common optimization algorithm in all of machine learning. It's common because it's sort of really simple to implement in a lot of cases, because each iteration can be quite fast, and because it tends to work in many cases a lot better than it has any right to work. So, you know, it has its problems. It converges very slowly in the worst case. So there are other algorithms that can converge orders of magnitude faster if you can afford them. But in the sense that you can apply it to almost any problem and get halfway reasonable results, it's like a really useful tool, a workhorse for machine learning. All right, so that was when the L0 term was missing, was 0. If L0 is not 0, we can do something slightly more complicated. We'll sample from the sum, from the 1 to capital T, and we'll always keep L0, right? And so if we take G to be the gradient of L0 at W plus T times the gradient of Li at W, where I is a random index uniform in 1 to capital T, you can go through almost the exact same argument that we went through up here to show that this has the correct expected value. Now, I want to point out, we could also just have sampled our index uniformly from 0 to t and scaled by t plus 1, instead of always keeping L0 and sampling only from the 1 to capital T. And that would work as well. And the reason that this is more common is that is something that I said earlier, which is often that we'll take L0 to be qualitatively different from L1 through L capital T. So L0 could have the prior, and L1 through T could be our data. And so we'll always keep the prior in our gradient estimate, and then we'll randomly sample a piece of data to put in our estimate. And this works especially if we have a strong prior, right? So if our prior is has a larger contribution to the loss than any single piece of data, then it's a good idea to always keep the prior in our estimate, because we're going to essentially reduce our variance that way. Let's see. Somebody wants to know what variable the expectation is with respect to in this block. Oh, this is with respect to the randomness in G, right? So the only thing that's stochastic in stochastic gradient descent is the random selection of an index into this sum. And so the expectation is with respect to the randomness in the algorithm, not with respect to the data or anything else. And so this expectation is just over the randomness in the gradient estimate G. Someone else is looking for an example of stochastic gradient descent. That's actually an excellent idea. I don't think that I can whip up an example out of my head right now, but I'll try to post one to Piazza as soon as I get a chance after class, meaning basically as soon as I get through the questions that people ask me after class. Oh, right. So somebody's asking what is the role of capital T here in stochastic gradient descent, and that just goes back to our sum of terms, right? So we had our optimization problem as a sum of terms, and capital T was the number of terms. And so if we go to an example, capital T here is the number of rows in our matrix A, right? Or in maximum likelihood, it's the number of data points. And this here is maybe the most common sum of terms type problem. And so often capital T in stochastic gradient descent will be the size of our data set, the total number of data points that we have. All right, so when people are defining stochastic gradient descent, I just wanted to mention that there's another convention that is common, and so you should be aware of it. A lot of times people will fold the factor capital T into the learning rate eta, right? And so the gradient descent update will become W is assigned to be W minus eta times the gradient of the ith term in the loss function. And you can see that that's the same algorithm because it's just we rescale eta to be the same as eta t in the original version. And in the version where there's a prior or another zeroth term in the sum, it would look like this. W is updated to be W minus eta times our gradient estimate scaled by t, so 1 over t times the gradient of the 0th term plus the gradient of the ith term. And again, it's the same algorithm, it's just a difference in the convention of how the learning rate is scaled. And so as long as you and whoever you're talking with agree on which convention you're using, there's no danger of confusion. But if you and whoever you're talking with don't agree, then you're going to have big confusion because you could have a data set with 1 million or 1 billion examples. And so if you're off by a factor of 1 billion on the learning rate you're talking about, that can be pretty important. All right. So parameter tuning. A bunch of people have been asking about this, and it's definitely a good question to ask about. So there's two things that we have to tune in stochastic gradient descent. One of them is the learning rate, eta, and the other is the total number of iterations, right? We just said repeat until we're tired, but in fact we don't do that, right? We have to have some automated way of saying when we're going to stop if we're going to implement this in an actual machine learning system. And in fact, it's actually even a little bit more complicated than that because often when you're running gradient descent, you want a bigger learning rate at the beginning and a smaller learning rate near the end. Why is that? Well, at the beginning, if we're far away from the optimum, then the gradient is going to be big. And so if the noise is either constant size or doesn't grow that quickly when you go far away from the optimum, then the gradient is going to be bigger than the noise, and so every sample is going to move you in the right direction, and you don't need to do too much averaging, right? So it's going to be something like this. If our optimum is here and we're way over here, right? then our gradient samples will, all look like, more or less the same vector, and we're going to be, sort of all pointing in the vague direction of the optimum. And so it doesn't matter which one we choose, we just want to take a big step in that direction. On the other hand, if we are close to the optimum, it could be the case, this could be, we'll call that W prime. So it could be that, we have one gradient sample pointing that way, another one pointing that way, and another one even pointing that way, right? And so, maybe on average, there are more of them pointing in the direction of the optimum, right? Because the expectation has to be, that direction, right? The expectation has to be pointing in the right direction. But the samples could have a lot more, it's a small gradient, and, you can see here, right? The spread here is actually about the same as the spread here, but the actual magnitude of the gradient is much smaller. And so when we're near the optimum, we effectively have to go slower in order to average out the noise. All right, so we have to tune the learning rate and how the learning rate decreases over time and when to stop. And so a lot of times, we're going to have our sum of terms come because we got a sample of data, and so we're going to be able to use that fact to create a way to do the tuning, and that is called a holdout set. So we have our loss function, which has, let's say, 1,000,000 terms in it, and we split it at random by sampling terms at random from the loss function into two pieces. And in expectation, both of the two pieces are the same because we sampled at random. We'll call the first piece the training set. Let's say that's 2/3 of our data. And the second piece, the holdout set, let's say that's 1/3 of our data. And then we run stochastic gradient descent only on the first piece, meaning that when we sample a random index, we only sample a random index in that first piece. We don't pay any attention for the moment to the held out parts. And we start with a large value of the learning rate, and we go for a while. And every so often we measure what is the loss on the held out part of our loss function. And so hopefully that'll be going down and going down. And at some point it's going to stop going down because our learning rate is too big. And so when that happens, we reduce our learning rate. Let's say we divide it by 2. Again, the factor is something that we have to tune, but 2 is a reasonable default value. And then we keep going and we keep going, and it goes down and goes down, and then at some point it stops going down because now our reduced learning rate is too big, and at that point we have it again and keep going. And then at some point, even after we have it, it's not gonna, the loss is gonna stop going down. And so at that point we're just gonna stop and return, say that we're done with stochastic gradient descent and return the last value of our parameters. Right, and this stopping when the holdout set, when L on the holdout set stops decreasing, that's the early stopping that we mentioned a few steps ago, a few paragraphs ago. So somebody is asking, why does stochastic gradient randomly pick an item from the sum? Well, so if we go back up here, right, our goal in designing stochastic gradient descent was to get a g whose expected value is equal to the true gradient, right? That's the thing that makes this derivation work, which says that the loss keeps going down on average. And so picking a term at random from the sum, right, according to this derivation here, shows that we do in fact achieve that that desired property, that the expected value of g is equal to the true gradient. There might be other ways to achieve it, but stochastic gradient descent, meaning picking a term at random from the sum, is a very general way to achieve it, and so it's a very common way to do it. People are, so the same question asks whether some data samples might not be used. Yes, that's right. If you have 1,000,000 data points and you only run 1,000 iterations of stochastic gradient descent, you're not going to use all of your samples. As a matter of fact, if you have 1,000,000 data points and you run 1,000,000 iterations of stochastic gradient descent, still probably you're not going to use all of your samples. You have to run maybe something like 30 million iterations to be relatively sure that you're gonna use all of your data points at least once. And that's fine, right? Stochastic gradient descent is not, it's not guaranteed to use every term in the sum, and it still works, right? There are theoretical results saying that stochastic gradient descent converges. And in order to make that happen, they have to assume something which winds up being basically that if I skip one term in the sum, it's not going to make a ridiculously large difference in the location of the optimum. If you are in that situation, if you have one term in the sum that is a lot more important than all of the other terms, well, you can take that term out of the sum and call it part of L0, right? And then you're always including it in every gradient calculation. And if you know that there are some terms that are much more important than others, but you don't know which ones they are, so you can't pull them out, then you're kind of sunk. Then stochastic gradient descent is going to have problems, because it might, like the question says, it might actually miss those terms, in which case it's going to miss some really important information. So a couple of questions about the holdout set. One is how to choose the data as the training set and the holdout set. And the answer is uniformly at random. So in other words, you randomly, out of all possible splits that are 1/3 of the data as your training set and 2/3 as training and 1/3 as holdout, out of all of those, uniformly at random, you pick one. And that's how you set which is the training set and which is the holdout set. Computationally, to do that, you can generate a random permutation of the integers 1 to 1,000,000 if there are 1,000,000 training examples, and then shuffle your data into that order and take the first 2/3 of it as the training set and the remaining 1/3 as the holdout set. Somebody's asking about the difference between a holdout set and a test set. That's an excellent question. We haven't mentioned, yes, okay. So this is maybe something that I should write up some lecture notes on, because it's actually kind of, it might take more than a short answer, but let me try and give a short answer. So, in machine learning, often our goal is, given a batch of training data, to produce a hypothesis, right? Like, let's say a parameter vector W that's going to do well on future data drawn from the same distribution. So, for example, I have a training set. Each element of the training set is an image that's labeled as either containing a cat picture or not, right? So it's a classification problem. And so my training set is 1,000,000 images, of which some are cats and some are not. And then the test set would be another 1,000,000 images that I don't have right now, but that I imagine I might get in the future. And I want to produce a classifier that does well on the future examples. My training set now, in order to run stochastic gradient descent, I can take my training set and split it into 2/3 that I keep as the actual training set, and another 1/3 that was originally part of my training set, but I'm holding it out of the training set. And so these are all data that I have at training time, and I'm intentionally holding part of it out of the training set. And the reason I'm doing that is to be able to do this this sort of parameter tuning in stochastic gradient or in some other algorithm, right? So training and holdout data are both data that you have at training time. You're going to actually run the optimization on the training data, and you're going to use the holdout data to determine something else. Like, for example, what is the learning rate, or when do I reduce my learning rate? And somebody mentions in the follow-up that this is related to cross-validation, and yes, that is. Maybe we'll talk about cross-validation a little bit later, but it's not the same. It's related, but not the same as cross-validation. Somebody wants to know how to choose the learning rate at the start. That is difficult. I don't know of a general way to do it. There are a lot of machine learning algorithms that attempt to automatically choose the learning rate. Adagrad, for example, is one of them. But I don't know of a general way to choose it. And that's one of the flaws of the stochastic gradient descent algorithm, that it's basically a parameter that you have to choose. So here, if you're doing this kind of parameter tuning, you just choose a fairly large initial learning rate. And if you chose too large, then you're not going to decrease the loss on the holdout set, and so you're going to keep having the learning rate until you do. Right, and so here, right, this makes it fairly easy in that you just have to choose something that's large enough. You don't want to choose it, you know, a factor of 23 billion too large, because then you're going to have it a whole lot of times before you get to something reasonable. But there's going to be a wide range of initial learning rates that works if you use this kind of strategy for parameter tuning. All right, so yeah. Tons of questions about stochastic gradient descent, which is great. Keep them coming, and let's move forward. All right, so we talked about getting an estimate of our gradient by looking at a single term in our sum, right? So we sampled uniformly at random a single index in our range from 1 to capital T. So we didn't have to choose just one. If we selected 2 indexes and averaged their gradients, essentially the same argument that we made before shows that that works, right? And in fact, it's fairly common to sample capital B indices at once, where B is much smaller than the total number of examples, but much larger than 1. So you might have 100 or 1,000 examples in your mini batch. And so when you do that, then the estimate of your gradient is T times the average within your batch of the gradient of the ith sample, right? And so when B is 1, this reduces to the previous case. And so when you're selecting a mini batch, there's actually a subtlety, which is whether you select the indices independently, meaning that you have a possibility of getting the same index twice in your mini batch, or without replacement, meaning that you sample uniformly among all possible mini batches that don't duplicate an index. The second is maybe more common. They both have the correct expected value. The second is slightly harder to analyze, but they both have the correct expected value. So why would we do a mini batch? It's a trade-off, right? So we make it more expensive to calculate the gradient estimate because we're doing B times as much work for a batch of size B, but we get a more accurate gradient estimate, which means we can choose a larger learning rate. Now, all else being equal, if we choose a mini batch of size B, that's going to reduce the variance of our gradient estimate by a factor of B and let us use a learning rate that's B times larger. Now, that seems like it's a wash, right? Because we're doing B times as much work to be able to choose a learning rate that's B times as large. But there's actually often a lot of good reasons to choose a mini batch. So, for one example, it could be the case that you can calculate B gradients for much cheaper than B times the cost of a single gradient. So you could ship everything off to a GPU and calculate all of them there on the GPU and ship back the average. And there, basically the time to invoke the GPU and wait for it to return, the time to communicate with the GPU is the limiting factor, rather than the actual time of computation. And so you wind up getting a savings because you only incur the overhead once per mini batch instead of once per sample. Another would be if you have a fast matrix library that you can use to calculate on your CPU a whole bunch of gradients at once. A last one is that a lot of fancier versions of stochastic gradient will calculate statistics of the gradient samples within each mini batch. So you could calculate, in addition to just the expected value of the gradient within the mini batch, you could calculate its variance and use that to help you select a learning rate. That's called batch normalization, in case you're interested in looking it up. And so mini batches can often be a really big win. All right, so there are a couple of problems with gradient descent and stochastic gradient descent when you use them in practice. We've already hit a few of them. One of them is that you converge only to a local optimum. One of them is that you have this difficult problem of choosing the parameters that you want to use. The single biggest one that we haven't mentioned yet is what's called conditioning. So there's a formal definition of a condition number, but it's actually much easier just to look at the pictures. So here is a well-conditioned problem. So we're trying to get to the minimum here. This is a contour plot of the different level sets of the function, and the contours are sort of, roundish, right? Whereas here, this is a poorly conditioned problem. It's actually essentially the same as this problem, except it's stretched out. And what happens is, if you're stretched out, the learning rate that you can choose is limited by your shortest dimension, your most squished dimension, and the rate of convergence is governed by the longest dimension, the one that's most stretched out. And so you can get very slow convergence. I mean, here this is not actually very badly conditioned. A really badly conditioned problem could have the long axis be something like, 10 to the 6, 1,000,000 times longer than the short axis, or even 1,000,000,000 times. So you can actually, in these two plots, they've indicated the progress of stochastic gradient descent, right, the different iterates, and you can see that in this well-conditioned problem, actually I think this is plain not stochastic gradient descent, and but the same thing is true for stochastic. And in this one, gradient descent basically heads straight for the minimum. It gets there after 1, 2, 3, 4 steps, more or less. Whereas with this one, the best you can do is just to sort of slowly step back and forth along the narrow dimension and gradually slide towards the optimum along the long dimension. And so if you look at this, here are these two problems with the convergence of gradient descent in the first well-conditioned problem. So this is how far away is the function value from the optimum. And this is the number of iterations. And you can see that problem 2 takes much longer than problem 1, even after you tune the learning rate well. And so this is something to watch out for in applications of gradient descent and stochastic gradient descent. If your gradient descent, or SGD, is converging really, really slowly, it might be the case, it might be a case that you have a bug in your code, but supposing that your code doesn't have bugs, it might be the case that you're in a really poorly conditioned problem. And maybe later in the course we'll talk about what the fixes to that might be. But for now, just recognizing the problem is a big step in the direction of fixing it. All right. Somebody wants to know, is there a general limit for how many examples there could be in a mini batch? No, there's no limit. You don't want to use a mini batch that's larger than the size of your training set, because then you basically might as well just use plain gradient descent. In practice, the limit is going to be whatever trick you're using for fast computation. So whatever size batch of examples it's convenient to ship off to your GPU at once. The other limit is that in mini batch SGD, you compute the gradient at all of these examples once, and then you take a step. And that means that your gradients are going to be a little bit out of date compared to plain stochastic gradient descent, right? Because the same number of examples, you would compute the gradient on one, take a short step, compute the gradient on the next, take a short step, and so forth. And so by the time you get halfway through your mini batch, plain SGD might have moved a fair distance. And so the mini batch might be taking the gradient at an out-of-date place. So those are the two factors that limit the size of the mini batch in practice. One is the worry about having stale, out-of-date gradients, and the other is practical considerations for how many gradients at once you can get a speed up for computing. Can I give an example of when we use mini batches? Yeah, a couple of people are asking about that. Well, I think I already did, right? So the example would be if you have something like a GPU that can compute multiple gradients at once faster than if you computed them each one at a time. Deep networks are a great example of that, right? People will use GPUs to calculate mini batches, typically 50 to 100 examples in a mini batch, and it's much faster to just you amortize the cost of communication with the GPU over the entire mini batch, and you get a big speed up that way. And also you get the option of using things like batch norm to help choose learning rates. All right, so that is what I wanted to say about gradient descent. And in the context, again, of what we've been talking about, the reason for gradient descent is to be able to solve a problem like maximum likelihood or maximum entropy, right? So we want to be able to compute the values of the parameters in a family of distributions that let us achieve certain properties, like explaining our data as well as possible. I wanted as well, we're going to release a short problem set today, the first short problem set of the mini. So I've gone ahead and released it on Canvas, and shortly I will post the same thing on Piazza. What I'd like to do is pause now for a few minutes and let everybody take a look at the problem, and please post any questions that you have about the problem on Piazza so that we can answer for everybody the common questions. So I'm just going to go ahead and pause our lecture stream, and I'll be back in a few minutes to talk about any common problems. All right, guys. There haven't been any questions on Piazza so far about the exercise. So I think maybe it's a good idea just to stop and change over to my office hours, and I'll continue to watch Piazza. Please ask questions about the assignment if you have any, or about anything else. And see you guys on Wednesday. Thanks.